see. Hello, hello. So today we're gonna work on improving the physics system as in previous episodes. So the last time we created a kind of sister function. Uh, uh, where we, instead of using a more particle-based system where the objects couldn't have rotations, we started implementing um, let's see, this is yeah. I'm just going to comment this. We started laying the bricks for actually using the rotation which we calculate here for our objects. Transform the inverse inertia tensors by the world matrix. Matrices, since it's plural. This is going to be the old function for checking AABBs against each other. New function to compare OBBs to static AABBs. And we would actually like something like this, where we try to get some information about where we find a collision. I think we will have a yeah, we could deprecate these two functions. Let's do AABB related. Then we do a new one, which is our OBBs. And this is basically what we will implement. We created this function last time that checks for collisions between our OBB and our yeah, I would like to rename these things, but it's something for a later day, maybe a simple task to do some late evening. Anyway, inside the checking algorithm, we want a function that gives us some information about the closest point. Right now we return the vector. Closest. Yeah, that's actually a better name. Closest point to point on OBB. We want to take in the same parameter here, but instead we want a bounding OBB reference box as well. Then we would like a method called float squared distance to point OBB, and we simply pass in the same information here. We create these two methods. This is by the manual of Ericsson from 2005. There might be new algorithms. Translated. Point on center is going to be math subtract the point vector from our box center. G vector result is equal to the box center. And we end up returning the result. And for each OBB axis, we iterate over them and calculate the distance that needs to be traversed on that axis by taking the dot product of the point on center, and we take the box and the axis. Let's see. We of course need to grab the data from it. There we go. If the distance is larger than the box half width on that axis, whoops. We set the distance to the actual half width. If it's lower than the half width, we simply set the distance to the negative version. And we set our result to math at scale vec3, which will be, we will pass in our result, we will pass in our axis, and we will scale it by the distance. And then we return the result. So let's test that. Let's see, collider index, maybe maybe this is fine. Whoops. Just checking out some stream stuff. Then we want to calculate our closest points on the yeah, we could do it calculated from the box center, for instance. Yeah, we might do that as a test. Wait a minute. We're actually not using that query method. Closest point on ABB. And we check the center. We could at least. Wait a minute. Okay, so this is where it gets sort of complicated. Yeah. Yeah, so if we want to check where we collide, let's see. Huh. Yeah, so we need to. So we have our bounding volume here. Let's see. Where are we having a problem? I introduced some error somewhere. Huh? Ah, I renamed the function. Of course. Closest point. Closest point. There we go. Yeah, so we have our bounding volume here. Um, yeah. mm, so yeah, we have some penetration of objects where we would like to know which is the point of contact. Uh, Yeah, so we want to be able to do something about that. Do we want the... Maybe we want... If we swap this around, let's just test that out. If we want the collision index here, center, and we pass in the OBB, we end up with a G vector point, which will be the closest point on the OBB to the center of whatever object we collided with. Yeah, but I'm not sure if we collide with an angled thing, there might be another point on that OBB that is closer to it. Yeah, that's not gonna work. Maybe if we grab the closest point on from the center of the OBB, and let's try to draw it. So if we imagine that we have an OBB here, let's see, yeah, you get the idea. Yeah, you get the idea. Anyway, we have an OBB here. We have the center in the middle here. And we want to, and we have a other box here. And they collide. You could ask, what is the closest point to this center? And then you could kind of calculate which internal axis is the one that has the biggest projection to or onto the vector. And maybe we want to do that. Let's try that at least. So we have a vector. Uh, yeah, let's just try this out. We don't know what we're doing. Anyway, we subtract vector center to points, and we pass in the static bounding box for the collision index, and we calculate a vector which we would like to normalize. No, let's not normalize it for now at least. So right here, we're doing subtract between the query. We need another parenthesis here. And let's try to dump it for debugging. Center to point back. Let's try that. Let's see. Let me see. Huh? What's happening? Oh, I'm pressing the wrong button. There we go. And actually, I would like. I'll put this off screen. Let's see. Collision index. We can't really interpret what we're seeing. Let's see. Yeah, we could add another. Let's see. Sometimes I do get another vector in the output, I think. Let's skip the ground. If collision index is equal to 0, we continue. So that we just do not get any information about the ground. Yeah, this tells me that there's a vector that extends some degree on the, this is the negative x and negative y, of course. And now it shifts. really amazed that this doesn't. It's actually not happening all the time, which I'd think that it would. So the collisions aren't getting registered correctly, I guess. I mean, this is kinda close. I mean, this should be registering collisions all the time. Do we not fill it in properly or what? Let's see if O is unlike 0. Let's do the same thing here. So well, it does register, it seems. It kinda, whoops. Okay, let me move this one up here. I mean, whoops, god damn it. I mean, it looks like it keeps on tracking collisions with keeps on tracking that, but it for some reason huh? That is pretty weird. I mean, the collision gets detected. I mean, and then it stops, which is perfectly alright. And huh. Oh, wait a minute, wait a minute, wait a minute. I'm so stupid. Oh my god. Staring me right in the face. This stupid bug. yeah, now we have information that is more like what we expected. Yeah, so the collision does get detected properly. Then we, excuse me. I'm really sorry about that. So yeah, we do get the vector away from the point. Maybe if we yeah, it's because we kind of walk backwards in terms of the actual point. Maybe if we do like this instead. Uh, this is definitely the way the sensor is pointing in terms of the points closest to. Let's see. We could also just store the closest point. Uh, maybe we save that. Let's see. We get a G vector point closest point on AABB, which will be exactly like this. So that's the closest point. What's the closest point on the OBB? On OBB, is equal to the query to closest point on OBB, closest point on ABB, and the bounding volume here. Maybe this is kind of stupid to do this way, but I'm just gonna roll with it. All right. Yeah. Now we have some information here. So it's definitely something far out to the left. So the point closest to the center with respect to the, let's see. So the closest point to the center on this ABB gets compared to the closest point on the OBB, which is probably something like here. We could also just do let's see if we do the axis of each OBB. Then we might, so for instance, if we have the closest point on the AABB to the center of the box here, and we have the vector that extends from the origin or center of the OBB to the AABB point, then if we find out which axis has the biggest dot product with that vector, we'd probably know which direction is more likely to be intersecting with the object. Let's see, so we still do the closest point on the AABB. But yeah, we want a test here where we iterate over each axis of the OBB. OBB. Oh my god, all these letters. I'm messing around with them, and I get word salad. So yeah, we have a float projection. Yeah. Actually, maybe we want this instead. Projection is equal to float. Let's just set it to 0, meaning that they are perpendicular to each other. Then we calculate what is the projection of vector 3 dot product between the vector center to point and then the dynamic bounding box axis. Let's see. Oh yeah, of course I have to grab the register here. If the dot product axis, and this is going to be an integer -1. If the dot product is larger than 0, we set the axis to, yeah, maybe we want actually a float projection as well. And then Maybe we just simply do not. Yeah, we still want the axis, but if we set the no. If the dot product is positive, we set the projection to the dot product. And also if the dot product is larger than the projection, which will be set to load min, we set the axis to I, and then we simply dump the information. Found axis is parallel oriented the same way. Let's see, we of course need that. And dot, let's see, projection here was dot prod. And we simply check for that. Oh, oops, we were too slow. Let's move that. So let's see. Yeah, it simply doesn't find a positive axis. Yeah, so this obviously has some. Oh, yeah. You of course have to swap the axis. That is why we're not getting some expected results. Axis 2, 1. What if I end up making it rotate there? Sometimes we actually hit a 0 as well. Let's see. So let's see if we retest it. And just try to interpret our information here. So as we rotate axis, so axis 1, axis 2, But it's rotated, of course. Yeah. So, yeah, it might be right. So right now, the X is pointing. This is the wall up here. Now it's really fucked. Oh, I'm sorry. Excuse my language. Yeah, this is definitely not the right way to do it. Yeah, so we want to find out a way where we are able to calculate a contact point. I do have a solution that we could use, but yeah. I mean, it's kind of wasteful to check every single corner. Because I mean, you could do that. You could take the every single corner of the OBB and check the distance of each corner to to um, compare that to oh, I'm really tired. I'm sorry. Compare that to whichever has the greatest penetration depth of each the greatest penetration depth of each corner, and then you'd know what from which corner had the greatest penetration depth. You'd know yeah, you'd know how the objects intersect and which point to get the correction from. Yeah, so we could do that. But it seems rather slow to iterate over 8 corners. Hmm. Maybe if we consider just the minimum and the maximum corners of the OBB. So if we consider the maximum corner and the minimum corner, whenever this thing collides with something, I mean, now the max corner is closest. Now the minimum corner is probably closest. Right now the minimum corner is by a large margin actually the closest. And if they are kind of equal, I mean, for instance here, the maximum is very close here. They will be, if they are equal or close to equal, the object is almost aligned. Then right now they are very close to equal and it's not aligned. I mean, the minimum is still closer. Maybe. So yeah, maybe we want to control the algorithm by that instead. Simply checking the we could do something like that. Test that out. check that out. So down here we actually do calculate, or we used to calculate the minimum. Yeah, we do. There we go. So half widths is equal to exactly that. Minimum is equal to the center there we go. And let's call it P for point, minimum and maximum point for this bounding volume. Let's place this outside here because we do not want to recalculate it every single iteration. So the distance between 2 points is equal to, I think, the first point minus the second point, and then each component of that squared. Yeah, as expected. So, but we first get distance min. We query for that. Squared distance to point, closest point on ABB between the minimum P and the static box with the collision index, and then the maximum max if the distance min is lower than the distance max. We simply know print in min is closer. Let's see. Else print in. Now it's max. Maybe we're colliding with too many objects here. Now it's max. Did I? Yeah. I forgot to change the variable. I knew something was wrong. Yeah. When we know it's the minimum, Uh, let's see. Yeah, now we at least can ask the system if but how does that help us? Yeah, this is going to be fairly complicated quite quickly. This is going to get really complicated. Hmm, this is somewhat a pickle. We could simply just iterate over all 8 corners. But that's so slow. That is simply so slow. Mm, let's see. Yeah. As for the YouTube series, I will have a reading break, I think. I'll be continuing onwards afterwards. Hopefully, uh, you found the first part of this helpful. The second part is just a lot of contemplating what to do. Alright, I'll be seeing you around.